Okay, so now we're moving into isomorphic and connected graphs that we started looking at today. So I've got up on the screen here a collection of 3 graphs up the top and then a collection of 3 down the bottom. So I want to draw your attention to how these 2 are the same graph and that each of these look very similar. But what makes an isomorphic graph? What makes it equivalent? And what does a graph actually do? So we have to go back to that question essentially and ask, what does a graph do? So first of all, what this graph here is telling us is that we've got these four points or 4 areas, and that from area A, let's say, you can get to area D and area C directly. But from area A, you can't get to B directly. It's only connected to, so A is only connected to D and C. Now D is directly connected, so D is directly connected to A, B, and C. So from D you can get to any of the other vertices. Okay, so then we come to C, and again, C, just like D, I can get to A, B, and D. And B, I can only get to D and C directly. I can go the long way, but I'm talking directly, so there's no edge connecting A and B. So if I come over to this second graph here, okay, so first of all, the rule for them being equivalent or isomorphic was that they had to have the same number of vertices and the same number of edges. So let's check. So we've got 1, 2, 3, 4 vertices. So 1, 2, 3, 4 vertices. And I've got 1, 2, 3, 4, 5 edges. 1, 2, 3, 4, 5 edges. So first tick for the number of edges and for the number of vertices. Okay, so let's go through and let's see if it's telling us the same information. So from A, I can get to D, yep, and C, perfect. From D, I need to be able to get to A, yep, C, and B. Awesome, so far so good. From C, remember on my screen here on the left, it's saying that I need to be able to get to A, which I can. Need to be able to get to B, which I can. And I need to be able to get to D. Again, I can. And last but not least, B. So B, I only want to be able to get to D directly, yep, and C directly, which I can. So second tick. So that means that by just satisfying those 2 criteria, remember that the number of vertices and edges is the same and that it contains the same information, so that travelling along the edges will result in the same thing, that I have an equivalent or isomorphic graph. So let's go on to our last one. So I've got 1, 2, 3, 4 vertices and 1, 2, 3, 4, 5 edges. So that's a first tick. So I've satisfied this criteria. The second one is that, I want to satisfy this on the left here. So it's telling me that I can get from a specific vertex to the other ones. Same is in the first graph. So A, I can get to D and C. D here, I can get to A, B, and C. C, I can get to A, B, and D. Beautiful. And B, I can only get to D and C and not A directly. Excellent. So that's both of those satisfying the criteria that they are equivalent to this first one. Okay, so these guys look the same as these 2 up here, So let's check to see if they are equivalent. So again, this graph and this graph are the same, exactly the same edges, same vertices, same positioning. So 1, 2, 3, 4 edges, vertices, and 1, 2, 3, 4, 5. Excellent. So satisfied this criteria here. But remember, I have to satisfy this second criteria as well. So A, I need to get to D, which I can, and A to C. Awesome. But then I've also got this edge here, which is telling me that from A I can get to B. And in the original graph I couldn't. So automatically that tells me that it's not equivalent. It's not an isomorphic graph because it contains different information. So edge vertex A here is actually degree 3. It's got 1, 2, 3 edges. So in the original graph it was only degree 2, so it's not isomorphic. So let's have a look at this other one and see if it is. So 1, 2, 3, 4 vertices and 1, 2, 3, 4, 5 edges. Awesome. Okay, what's the information telling us? So A, I can get to D, and A, I can get to C, but here again, we've got a line A to B, and we don't have an edge A to B. So again, different information, so it's not an equivalent or isomorphic graph. So that's what it's talking about when it's asking you to identify isomorphic graphs. So remember, there's 2 criteria that you need to justify. So it's both that the number of vertices and edges is the same, but also that the information is the same. Okay, let's go down and let's start talking now about connected graphs and what that means. So a connected graph means that from like all the vertices are connected essentially. So you can get from one to another in the graph. So this example is of a connected graph. So see how if I'm at point A, I can get to every other vertex. Another example would be this one. So A, B, C, D. Now, when it says that you can get from one vertex to all the others, they don't have to be directly connected as long as they can follow a chain of edges to get there. So A can get to D, it is still a connected graph, even though it's not directly connected to every other element in that graph. And last but not least, another connected graph, just so you've got a good number of examples. So again, a connected graph where this element B may not be connected to these 2 elements directly, these 2 vertices directly, still connected via this vertex C. So again, still a connected graph. However, if we made a few changes and we had something like this, where this vertex out here was isolated, so this is not connected. Because you cannot in any way get from this vertex to the rest of the vertices, and vice versa. You can't get from this vertex out to this one either, because there's no edge joining them. Again, another example would be something like this. Whoa. Something like that, and you've got this isolated vertex out here. Again, not connected, you've got a vertex out on its own that you can't get to. And last but not least, even if you had something like this, where you've got no isolated vertices, like you haven't got an isolated vertex, again, because you can't get, it's the one graph, but you can't get from vertex A to vertex C, it's still classified as being not connected. Got to stop clicking that button. So not connected. Now, some places where connected graphs may come into play is, road planning, electrical circuits, communication systems. Because if you've got a missing connection, so if one of your computer terminals isn't plugged into all the rest on the system, you're going to be either missing information or they're not going to receive any of that information. So these can actually be really important in day-to-day life. Okay, let's leave it there. The next video I'm going to start talking about these connected graphs and bridges in them.